Let's now venture into the deep waters of probability. Probability is the likelihood that an event is going to occur. It's usually listed between 0 and 1, or sometimes you see it as a percentage from 0 to 100. Probability is related to something called relative frequency. Well, to talk about relative frequency, we first have to define some terms. N, capital N, is the total number of trials, and N of A is the number of times we see a certain event A occurred. For example, if we do 100 trials and our event A is the number of heads we see when we flip a coin, so what we're looking at is the flipping of a coin, and we're looking at the number of times heads occurs, well, our relative frequency, the amount we observe, which is the number of heads divided by the total number of trials, goes towards or approaches our probability when N is large. If I have a small n, like only 10 trials, well, I could have 8 or 9 heads in 10 trials, and you'd say, well, most likely then the probability is 80 or 90% heads. Well, if we make N 10,000 or 100,000 or 1,000,000, we're very unlikely to get 80,000 or 8 million heads when our N is large. Our relative frequency will approach our probability when the number of trials is large. We'll see that in a graph in one moment. Well, we just talked about how probability and relative frequency are related. As the number of trials grows larger and larger and larger towards infinity, the relative frequency, which again is the fraction of the number of times we see our event occur divided by the number of trials, approaches probability. And the simplest example I can think of is the probability of getting a head when you flip a coin. That's going to be 50%. You expect about half the time, well, exactly half the time of the number of trials to be heads. But if you do just 3 trials, you could get all tails. Or if you did 12 trials, you could still get all tails or 1 or 2 heads only. But as you go to 1,000, 10,000, 20,000 trials, you would expect our observed number of heads divided by number of trials to approach 50%. And that's what this graph is showing. As the number of trials is small, like 3, 4, or 5 trials, we can be way away from our actual probability. But as the number of trials gets closer and closer, or higher and higher, eventually we're approaching 50%, which is the expected probability. The relative frequency approaches this probability as the number of trials grows larger and larger. Let us now talk of theoretical probability. Well, in theoretical probability, the circumstances of each trial and each experiment are identical. One of the first things we have to define with experimental probability is the sample space. What is the sample space? It's all possible outcomes of our experiment. For example, if we are rolling a die, a six-faced number cube, our sample space is the individual numbers. We could get a 1, a 2, a 3, a 4, a 5, or a 6 when we roll a die. For a coin, our possible outcomes are heads or tails. For a deck of cards, a standard deck of cards has 52 different cards. And so each of these is the sample space. Now we can talk about the laws of probability. We already know that the sample space, U, is the set of every possible outcome. An event is any subset of U. So if, for example, this could be all the students in the school, and the subset could be those who bring their lunch to school. What is the probability of a specific event A? Well, it's NA over NU, which is, NA is the number of outcomes in which the event A occurs divided by the total number of outcomes in the sample space. NU is the whole sample space. Here are some axioms of probability. Here are 3 axioms of probability. Probability of event A occurring is always going to be between 0 and 1. If we have a probability of some event that cannot occur, we have a probability of 0. In other words, if event A cannot occur, then our probability of event A occurring is 0. It can never occur. probability of something that always happens is 100%. So if event A is equal to our sample space, that implies that the probability of event A is 100% or 1, and it's a certainty that it will occur. If two subsets of our sample space, A and B, are mutually exclusive, the word here is mutually exclusive, and when you hear mutually exclusive, I want you to think one or the other. They cannot happen at the same time. Then the probability of A union B, or A or B happening, is simply the probability of A plus the probability of B. Let's now talk about probability and Venn diagrams. The first one I want to talk about is the complement of subset A, which would be A prime. In quotes here we have the set of elements that do not belong to A are the complement of A. So if here is our sample space in the Venn diagram U, our subset is A, anything in red here is A prime, or the complement of A, is anything not in A. Of course, if that's the case, then we can also say that the probability of A prime, or the complement of A, is going to equal to 1, which is the total probability of everything, minus the probability of A. We can see also that the probability of A plus probability of A prime is going to equal 1. Either way, you'll be okay. The intersection of A and B is written like this: A with a sort of an A without the bar across, B. A and B, or A intersection B, is the set of elements belonging to both A and B. In our Venn diagram here, we have a sample space. We have two subsets, A and B. Where they overlap is A and B, or A intersection with B is right here in the middle. Continuing with probability and Venn diagrams, the union of A and B is written A with that the U sign, B, and it is the set of elements belonging to set A or set B, or set A and B. It's anything in A or B, or in both of them. So here is the picture for our sample space U and our subsets A and B, anything in A or B, or in the overlap. But we have to be careful when considering the probability of A union B, because if we count A and then we count B again, then we're overcounting this we're counting this overlap twice. So it turns out that the probability of A or B is equal to the probability of A plus the probability of B minus 1 time the overlap there, because we've counted it twice. So you must remember this formula. Probability of A union B is probability of A plus probability of B minus that overlap, because we've counted it twice. In our last Venn diagram of probability, we have mutually exclusive events, and I need you to remember this picture for mutually exclusive events. Notice in the subsets A and B in sample space U, there's no overlap. In other words, the event A and B, or A intersection B, is the null set. So the probability of having A intersect with B is 0. Well, we know the probability of A union B is probability of A plus probability of B minus, usually we say minus the probability of A and B. But with mutually exclusive events, the probability of A intersection with B is 0. So it's just simplified to this. What are mutually exclusive events? Remember, the phrase that you need to know is one or the other. If you have a flip of a coin, you can either get heads or tails. If you have a basketball game at 8 and the movie starts at 8, you can go to the basketball game or the movies. You can't go to both. They're mutually exclusive.